Hi students, very good morning. In our last class, we are discussing allowed energy levels or allowed energy states. According to the allowed energy states, up to we calculate energy. Allowed energy E is equal to, what is the value known? H cut square pi square by 2m L square into something. So, depending on possibilities, we can explain degree of degeneracy or fold. Degree of folds or degeneracy are explained. So, according to the ground state, we have ground state. We are taking nx value is equal to 1, ny value is equal to 1, nz value is equal to 1. Based on that, the ground state energy can be obtained as 3 by 2 h cut square 3 by 2 h cut square pi square by m L square. This is the ground state energy level value. After that, next excited state you can take as n is equal to ny is equal to 1, nz is equal to 1. Otherwise 1, 2, 1. Otherwise 1, 1, 2. How many possibilities are there? You have 3 possibilities. Nothing but 3-fold symmetry is occurred. So degree of degeneracy is 3. You can substitute in this equation. We get 1 square plus 1 square 2. 2 plus 4 square 6. Nothing but the first energy state value is 4 plus 1 5. 5 plus 1 6. 6 by, what is the value? 6 by 2 into h cut square pi square by m L square. Nothing but 3 times of h cut square pi square by m L square. After that, you can, what is the possibility you can take as, suppose nx value is equal to 5, ny value, otherwise you can take 3 also. 3, ny value can be taken as 3, nz value can be taken as, this is the example case you can take. So 3 square plus 3 square 9 plus, 3 square 9 plus 9 18, 18 plus 9 27. So they have the energy level, energy is 27 by 2 h cut square pi square by m L square. H cut square pi square by m L square. This can be written in terms of ground state. 9 3s 27. So 9 into 3 by 2 h cut square pi square by m L square. So 9 times of ground state energy. Here ground state energy equal 3 by 2 h cut square pi square by m L square. In that point of view, you can take the values nx is equal to 3, ny is equal to 3, nz is equal to 3. You get the energy of particular that state can be 9 times of ground state. How many possibilities? This is the first possibility. Second possibility, same value is occurred 5 1 1. 25 plus 1 26, 26 plus 1 27, 1 5 1 1 1 5. Here 3 possibilities are there, here 1 more possibility is there. So total degree of degeneracy can be taken as 4-fold symmetry. 4-fold degrees of degeneracy are occurred. So in that way you can calculate up to the 4-fold degeneracy rate according to the values of nx, ny, nz. This is the allowed energy levels. Particularly first you can calculate with respect to one-dimensional point of view, you can calculate nothing but especially we are deriving Schrodinger's wave equation reduced to find the energy with respect to x direction, after that y direction, after that z direction. So these are 3 are mixed. You can get the 3-fold, nothing but 3-dimensional, and ex plus ey plus ez. Total energy can be obtained for ground state is equal to, particularly you can get the ground state is equal to n, standard expression is En is equal to h cut square pi square by 2m L square into nx square plus ny square plus nz square. This is the total energy of allowed region, total energy of allowed region. That is the first part. Up to this you get the equations are 22 equations we can derive. We are assuming 22 equation up to allowed region. That part continues to next topic, that is called as density of allowed regions. The next part, in allowed regions you can calculate the density of allowed region. Each and everyone knows what is density. Density is nothing but the ratio of mass and volume of the given system or given body of the given particle. So based on that you can derive it density of allowed states. So the next topic belongs to allowed region is called as density of allowed states. Density of allowed state. Density of allowed states. So the density of allowed state can be explained. Let you can consider G of E into dE. G of E into dE be the density of allowed states in between. This density of allowed state you can take in between E and E plus dE region. E and E plus dE region. So you can consider D of E. You can consider D of E is the total number of state. D of E is nothing but you can get the total number of allowed states. Total number of allowed state. G of E and D of E is nothing but density of allowed state, particularly in between the energy levels E to E plus D. In a similar way, D of E is nothing but total number of states counted in the previous section, particularly energy E. Particularly energy E. So at the particular energy E, D of E can be taken as integral of G of E into dE. The ground state energy can be taken as 0 up to the energy you can calculate E. So that is the density of allowed states is equal to integral 0 to E dG of E into dE. On differentiating these states you can get the result. This equation can be taken as 23. This equation can be taken as 23. This equation on differentiating we get G of E value. G of E is equal to differentiating. G of E is equal to d by dE of capital D of E. What is capital D of D? Total number of allowed states, in particular the energy E, that is called as. So this can be taken as your equation number 24. According to the equation 19, what is the equation 19? With respect to energy, energy is equal to h cut square by 2ml square into nx square plus ny square plus nz square. From equation number 19 you get, from equation number 19, finally you get the result is nx square plus ny square plus nz square value is equal to 2ml square by h cut square pi square into E. Finally get nx square plus ny square plus nz square is equal to 2ml square by h cut square into pi square into E. That is the from equation number 19. Particularly from this equation you can represent the spherical radius can be represented as from this equation you can take as spherical radius can be represented as 2ml square E by h cut square pi square whole power 3 by 2 whole power with respect to cubical form, this is 1 by 2 whole power 1 by 2, particularly in the space region. In the space region, that equation represents the radius of the spherical part. Radius of the spherical part. So sphere radius can be taken as 2mel square by pi square h cut square whole power 1 by 2. So it can be taken as space region, particularly they have n-fold degeneracy, n space. So this equation can be substituted in the equation number 24. You get the result is d of E is equal to 1 by 8 times of 4 pi by 3 into 2mel square by h cut square pi square whole power 3 by 2. That is density. Density is equal to mass by volume. On that way you can substitute. Spherical radius is equal to 4/3 pi r cube. 4/3 pi r cube. So 4/3 pi r in place of spherical radius is can be taken as this is r, whole cube is nothing but 3 by 2. 3 by 2 because we are taking the cubical box. So you can taking the cubical box. On calculating you get the result is v by 6 pi square into 2me by h cut square whole power 3 by 2. So the density of states can be taken as d of E is equal to v by 6 pi square into 2me by h cut square whole power 3 by 2. This equation can be taken as your equation number 6. So we are assuming cubical box of length L. So volume of the box is capital V is equal to L cube. Volume of the box can be taken as L cube. Then density of allowed region. So particularly density of allowed regions can be taken as, so density of allowed states G of E is equal to V by 4 pi square into 2m by h cut square whole power 3 by 2 into e power 1 by 2. This equation can be taken as your equation number 27. So the density of states E of E is equal to V by 4 pi square into 2m by h cut square whole power 3 by 2 times of root E or e power 1 by 2. So that equation represents the states without including the factor of 2 for spin up and down degeneracy. This equation, the density of states without including the spin factors. Spin factor nothing but every electron which can occupies in two states of degeneracy with respect to spin point of view. So the spin can be taken as upward, S can be taken as plus half. The spin can be taken as downward, that can be taken as minus half. Without taking the spin point of view, the density of allowed regions can be taken as V by 4 pi square into 2m by h cut square whole power 3 by 2 into e power 1 by 2. Suppose we can take the spin values also. You can take the spin of the system can be taken, particularly electron. You can take the occupation based on the spin point of view, including the spin. Up to the equation number 7, you are not considering the spin factor. Suppose you can take the spin factor. You can take the spin factor, or including the spin factor, the density of states can be taken as G of E is equal to V by 4 pi square into 2m by h cot square, whole power 3 by 2 into e power also 3 by 2 e power here only 1 by 2, I am mistaken, here 2 pi square. With respect, you can take the spin values also based on spin factors. Here equation number 28. Equation number 28 including the spin factor. Equation number 29 without taking spin factor. So these two equations represents the density of allowed regions. The two values are indicating the density of allowed regions. Up to this, you are completing the first topic, that is called as allowed energy states or allowed energy regions. So allowed energy regions part is completed. So up to equation number 28, you must derive is the allowed regions part is completed. After completion of first part, the next topic is Fermi level. The next topic is Fermi level. What is Fermi level? So, according to the topic, we are explaining particularly energy levels. So, we are explaining present the topic is Fermi level is nothing but energy level. Fermi energy level, which is indicated by letter E suffix F. You can take either capital letter or small letter. So present topic, the second topic in the chapter number 2 is Fermi energy levels. Just you recall it in the class 1, 2 and 3. According to the chapter number 2, I think this is the third class. Up to the third class, every class point of view, I am explaining or define the particularly Fermi energy level. What is Fermi energy level? So the basic definition. Actually in the lower standard intermediate point of view, otherwise degree 4th paper point of view. Semiconductor chapter, we are explaining the Fermi energy level. This topic is also existed in our M.Sc level. Fermi energy level, which is indicated by EM, either capital or small. We can indicate this, no doubt. So what is Fermi energy level? So lowest standard point of view, otherwise up to last class point of view, I am explaining the or discussed the what is Fermi energy level. The basic definition. The Fermi energy level must and should be explained at absolute temperature. No doubt. So Fermi energy level must and should be explained at absolute temperature, that is at 0 Kelvin. Particularly you can explain at 0 Kelvin. What is Fermi energy level? The basic definition of Fermi energy level from the bottom class point of view, at absolute temperature, the topmost completely filled energy level. The topmost completely filled particularly at absolute temperature. that energy level can be called as Fermi energy level. So based on Fermi energy level, what you can conclude that, suppose you can take this part is Fermi energy level, nothing but the topmost completely filled energy level is called as Fermi energy. So bottom energy levels, how many energy levels are there? These all energy levels are particularly completely filled energy levels, completely filled energy levels. The above the Fermi energy level is unoccupied or completely filled energy levels. So what the Fermi energy level is there? That particular Fermi energy level is nothing but the topmost completely filled energy level at a particularly at absolute temperature. The topmost filled level can be taken as Fermi energy level. From this diagram point of view, you can conclude that, what would you conclude that? Bottom the energy levels of the Fermi level, or each and every energy level must be completely filled. Above the energy level is unoccupied energy levels. So you can consider the allowed energy levels. Particularly you are considered allowed energy levels or states. You can consider the energy levels or energy states. At what temperature you can explain? These energy levels can be taken at absolute temperature, nothing but at 0 Kelvin. So at 0 Kelvin you can assume allowed energy levels. You can assume allowed energy levels. At this condition you can add the electron. Particularly at this condition we can add the electrons to the energy levels. So at absolute temperature you can assume the allowed energy levels. At that condition you can assume, what you assume? You can add the electrons to the energy levels. At this condition all electrons are first filled the ground state. After that next exit state. By using the Pauli's exclusion principle and Hund's point of view, you can fill the, first we fill the ground state and then higher excited state will be filled until the last electron is to be added to the level. Above which all energy levels where the last electron is completely filled. So at that point of view, below energy levels must and should be completely filled levels, and above energy levels are particularly unoccupied energy levels. The last electron is added to the level above which all other states are unoccupied levels. At what the final energy level is completely filled. That completely filled level can be taken as Fermi energy level. At this point of view, you can draw a graph between density of allowed state versus energy. You can draw the graph in between density of allowed states between energy. So you can draw a graph. On x-axis you can take the energy, capital E, and y-axis you can take density of allowed states. So you can draw the graph between, particularly at 0 Kelvin, the energy is increases, density also increases, like this, particularly at 3 degrees Kelvin. particularly at T degrees, the T value must and should be equal to 0 Kelvin. The T value must and should be equal to 0. Other than at greater than 0 Kelvin, you can take the absolute temperature, you can increase the temperature, the density of states are filled like this. This is indicated at P value greater than 0 Kelvin. So the dotted line indicates the temperature is assumed at greater than 0 degrees centigrade. The solid line is indicated particularly at 0 Kelvin. So where the 0 Kelvin, you can draw a vertical line like this. Vertical line like this. Particular this energy can be called as Fermi energy level. That is called as Fermi energy level. So at this up to this energy level, the all energy states are occupied with respect to the given number of electrons. This shaded region indicates completely filled levels. This shaded region indicates completely filled levels. Completely filled levels. So Fermi energy level can be defined as the energy of the topmost filled level and is calculated from the number of free electrons. This Fermi energy level can be calculated. Fermi energy level can be calculated from the total number of free electrons. Total number of free electrons, capital N, can be taken as total number of electrons. You can calculate it. The total number of electrons can be taken as N value is equal to integral of G of E into dE. G of E into dE. That value here, energy can be taken as from 0 state to total energy E. So this equation, you know that G of E value is in the previous point of view, you can calculate it. That value can be substituted in this equation. You get the result is V by 3 pi square into 2m by h cut square whole power 3 by 2 into Fermi energy level, especially e power 3 by 2 is there, particular in that point of view, Fermi energy level e 3 power. This equation can be taken as, from this equation, the Fermi energy level EF value can be taken as h cut square by 2m into, on the calculation you get the result, EF value is equal to h cut square by 2m into 3 pi square capital N by V whole power 2 by 3. This equation can be taken as continuous equation. That value is 29. So based on number of free electrons in the Fermi energy level point of view, the number of electrons can be taken as integral of density of state. Based on density of states, you can calculate, you get the result is V by 3 pi square into 2m by h cut square whole power 3 by 2 into, at this condition Fermi energy level can be taken. So Fermi energy level whole power 3 by 2. On this calculation, you get the Fermi energy level is h cut square by 2m into 3 pi square n by v whole power 2 by 3 e by 3. This equation leads the Fermi energy level surface. Particularly, you can represent the wave vector. Point of view. This equation in Fermi energy level wave vector, EF value is equal to h cut square by 2m. h cut square by 2m into kf square. Here kf is nothing but Fermi energy level wave vector. Kf is nothing but Fermi wave vector. Fermi wave vector. It can be taken as from the equation Kf is equal to 3 pi square capital N by V whole power 1 by 3. This equation can be taken as equation number 30. That is called as Fermi wave vector. Fermi wave vector Kf is equal to 3 pi square N by V whole power 1 by 3. Based on that, we can calculate the velocity. Based on that, we can calculate the velocity of Fermi electrons. Each and everyone knows if any particle or any electron is moving, they have the momentum. According to basic definition, momentum P is equal to mass into velocity. P is equal to mass into velocity. According to quantum mechanics point of view, momentum can be taken as P is equal to h cut k. So from this equation, velocity V is equal to h cut k by m. H cut k by m. So you know k value is also well known calculation from equation number 30. You can substitute in this equation, you get the velocity of the electron is equal to h cut by m into k is nothing but 3 pi square n by v whole power 1 by 3. This equation can be taken as 31. That is called as velocity of the electron in Fermi energy level. So that momentum or moving electron has the some velocity. That velocity of the Fermi electron can be taken as h cut m by 3 pi square n by v. 3 pi square n by v whole power 1 by 3. That is called as velocity of the Fermi electron. On that point of view, you can calculate Fermi temperature. Based on that, you can calculate Fermi temperature. So according to the Fermi and energy level point of view, energy E is equal to some Boltzmann constant into T, kBT. From this equation, you can calculate the Fermi temperature. So Fermi temperature Tf is equal to E by kB. Fermi temperature is equal to E by kB. So you can calculate the E value in the past. You can substitute in this equation. You get h cut square kf square by 2m into kb. Kb is nothing but Boltzmann's constant. So Tf is equal to Ef by kb. So kf square. So each and everyone knows kfl is there. You can calculate the kf square and substitute in this equation. You get the result is h cut square by 2m into 3 pi square n by v whole power 2 by 3. 3 pi square n by whole power 3 by 3. Here kV is missing, so kV. This is called as Fermi temperature. This equation can be taken as 32. That equation can be taken as 32. So this is the Fermi energy level electron velocity. This is the temperature, particularly Fermi temperature. So this is the expression for Fermi energy level temperature. So Fermi energy level must and should be explained at absolute temperature. So based on that, you can take the graphical system. You can draw the density of states versus energy level. The shaded region or each and every one indicates the completely filled electron states. You can give the thermal energy. How the thermal energy is given to the temperature? By using the room temperature, by raising the temperature of the room, anything. So based on that, the electrons in the ground state absorbed the energy. So absorbed energy of the electron, those are not in stable state, those are moving state. Based on that momentum, I am explaining the velocity, momentum and temperature of the electrons in the higher states. Temperature of the higher states at that condition, particularly at absolute temperature. All allowed states or energies up to Fermi energy level will be occupied, particularly at what temperature? At absolute temperature, particularly at absolute temperature, the top, the at absolute temperature, all allowed energy states, energy up to Fermi energy level, energy up to Fermi level, all are occupied, states. At absolute temperature, energy up to Fermi energy level, all are occupied states. If the temperature of the system increases, the variation of electron energy is provided by thermal energy of the crystal. This value is explained particularly at absolute temperature. Suppose you can increase the temperature. Suppose temperature increases. You can increase the temperature. The variation of electron energy, particularly the variation of electron energy, but is provided. Energy is provided by thermal energy. Thermal energy. At what condition thermal energy is absorbed? Thermal energy by the crystal. Thermal energy of the crystal. So you can increase the temperature. The energy is absorbed by the thermal energy. That energy is absorbed from the crystal. So on that thermal energy, the electrons can be moved. Now that moment energy, particularly the moment velocity, can be taken as h cut by m into 3 pi square n by v whole power 1 by 3. And that particular temperature is h cut square by 2m into kV into 3 pi square n by v whole power 2 by 3. The variation is very, very small. This variation is by absorption the thermal energy, the variation with respect to Fermi energy level and increasing the temperature point of view, that variation is very, very, very small as compared to the electron energy itself. The energy distribution can only changes very slightly when the temperature is higher than 0 Kelvin. So you can increase the temperature at 0 Kelvin. That variation nothing but absorbs the energy from the thermal point of view. That variation is very, very small, nothing but at 0 Kelvin, and higher than 0 Kelvin the variation is very, very, very small, nothing but there is no minor values changes. Minor values can be changes. Only electron with energy higher the Fermi energy level will change their states, rising the temperature because of thermal energy will sufficient to excite electron with lower energy state to unoccupied state. This is shown by dotted lines at the condition. In the graph you can represent the dotted lines. Suppose you can provide the thermal energy. Suppose we can provide the thermal energy in the lower energy levels, electron. Suppose this is Fermi energy level. So from Fermi energy level to this energy level, my assumption can be taken as 10 electron volts energy gap is there. So you can absorb the thermal energy by using the room temperature point of view, thermal energy. This thermal energy I am giving some 11 electron volts. Up to the thermal point of view, up to the ground state to Fermi energy level point of view, the thermal energy you are applying 11 electron volts. In that 11 electron volts, 10 electron volts is used to cross the Fermi energy level. One more 1 electron volt is there, it goes to the higher level. So you can you know the Fermi energy level value. Based on that Fermi energy level point of view, more than the Fermi energy level energy, we can supply by using the thermal energy. By supplying the thermal energy greater than the Fermi energy level, those electrons are going to the higher energy levels. Those are electrons are going to the higher energy levels. At the state, the electrons are unstable state. At some time going running, finally those electrons must and should be come back to its original position by emitting of absorbed energy. That emission of energy and absorption of energy both are always be equal according to the energy level diagram point of view. So that absorption energy and emitted energy always be equal. So this is indicated according to the density of state. You can draw the dotted line. That is Fermi energy level position. That is Fermi energy level positions. So up to this second topic is completed. What is the second topic? Fermi energy level. What is Fermi energy level? The Fermi energy level must and should be explained at absolute temperature only. At absolute temperature, the topmost completely filled energy level is called as Fermi energy level. Up to the Fermi energy level point of view, below the energy levels, each and everyone is completely occupied by the electrons. Above the Fermi energy level, those are unoccupied states. So at absolute temperature, the topmost completely filled energy level is called as Fermi energy level. So you can give the extra energy. Generally thermal energy is very low energy. That energy is not sufficient to go the electron from one state to another. Suppose the thermal energy is very high. Suppose our assumption, the thermal energy is very high. If that energy is absorbed by the lower states of Fermi energy level, those electrons absorb the thermal energy. Those are going to the higher energy levels. Nothing but they can cross the Fermi energy level. So based on thermal energy, some of the electrons absorb the thermal point of view. Those are going to the higher excited state. After some interval of time, those are in unstable state, where immediately those are come back to its original position by emitting off. What the amount of energy is absorbed, total amount of energy is released in the form of radiation. That is called as Fermi energy level. So up to the point we are completing second topic, that is called as Fermi energy level. So after completion of Fermi energy level, we are going to the main very important topic, that is called as Fermi-Dirac statistics. Fermi-Dirac statistics. So in starting point of view, I am explaining what are fermions. The particles obeys the Fermi-Dirac statistics is called as fermions. Why you are using or introducing the next topic, Fermi-Dirac statistics? Up to the topic or point, you are explaining particularly the electrons are filled at absolute temperature, otherwise below the absolute temperature you are clearly explaining. So up to the point Fermi energy level, you are explaining at the absolute temperature, otherwise below the absolute temperature you are explaining very clearly. What about above the absolute temperature? So above the absolute temperature, how electrons are filled energies in the level, filled energy levels, how electrons are occupied. That occupied energy levels above the Fermi energy level, you are explaining the new term or new quantity point of view. You are explaining the next and very important one is Fermi-Dirac statistics. So based on our assumption point of view, our Fermi-Dirac statistics clearly explain the energy levels of electrons are occupied the energy levels above the Fermi energy level. Particularly above the absolute temperature. So the main important point is, in order to explain distribution of electrons above the absolute temperature. Distribution of electrons above the absolute temperature. That point clearly explained by Fermi Dirac statistics. The main very important topic in our chapter is also known as Fermi Dirac statistics. The topic you are explained or explaining in our next class. Okay. The next topic we are explaining in our next class. The topic is Fermi Dirac statistics. Fermi Dirac. So this topic is introduced by Dirac. The scientist name is Dirac. The next topic is Fermi Dirac statistics. So this topic is very important in our present chapter, unit number 2, chapter number 2, very important. This chapter or this topic is explained in our next class.